Hello, everybody. Welcome to the second online lecture of our post-apocalypse combinatorics class. Um, the first lecture was the lecture for Monday, March 23rd. This is the lecture for Wednesday, March 25th. So I do want to remind you that if you have not watched the lecture for Monday, March 23rd, you should also take a look at that lecture as well, right? At the beginning of that lecture, I spend quite a bit of time talking about how the course is going to work from this point forward, right, to the end of the semester, now that we have to, now that the campus has been completely closed and we have to do everything online now. So that has important information at the beginning of the lecture about those sorts of topics. And then the second half of that first video lecture is really genuine combinatorics lecture. There we were talking about, I was talking about finite probabilities, which we had just briefly discussed before spring break, but I continued with that discussion on Monday, and we're going to finish with our last example of finite probability today, and then we're going to start a new topic, which a little bit more advanced topic in combinatorics, but also an important topic not just for combinatorics but for mathematics in general. So again, if you have not watched Monday's lecture, please, the lecture for Monday, March 23rd, please take the time to look at that. Okay, I wanted to point out just a couple of things that are important, that are going to be important quickly here. Remember the homework number 4, which has been assigned for quite some time now, that is going to be due on Monday, March the 30th. So there's an announcement in Blackboard, right, that has instructions for how you're going to submit that assignment. Basically, what you're going to do is write your work, of course, on paper like you have been doing, and then you want to scan that work into a PDF file. And you can do that if you have a scanner, of course, you can do that easily. But if you don't, you can also do that with your cell phone. And there are instructions in this announcement here in Blackboard to help you with that task of scanning your homework. And then you're going to email that to me, and that's how I'm going to grade it, right? Okay, so that first homework is due on, again, on Monday, March the 30th, so that's coming up now pretty quickly. So if you have questions about this homework, either the problems in the homework or how to get this scanned and emailed to me, you'll email me at my regular address. Please contact me, right? So you can email me just questions, right, at my normal email address, or you can call me also at my office phone number. Those my email and my office phone number are on the syllabus, of course, the class syllabus. So so you can contact me in those ways. Even though I'm not on campus, I can still receive calls at my office phone number. So you can call that number, or you can visit my virtual office hours that I'm holding each day. And here are the instructions for the virtual office hours, right? We're going to be conducting those via Zoom. So if you look at this announcement, that has the instructions for how you can join my virtual office hours meetings, right? That are being held on Zoom. Okay, so that's how you're going to have to, contact me if you need to talk to me, right? Email, phone, or Zoom office hours. Be sure now that you submit this homework, even if you don't have it completely finished. Again, it's due on March the 30th, but you can email it to me anytime before midnight on March the 30th. But be sure you submit whatever you have, even if you don't have it completely finished, because you need to have at least a trial run there of how to scan documents and email them to me. Because this is how we're going to have to be submitting homework for the rest of the semester, and also taking tests this semester. And speaking of tests, we had a test scheduled for April the 1st, but that test has been postponed until April the 10th, because I want to give us plenty of time to make sure that we know how to, again, to scan things and email them to me right before we take our first test in this online format. Okay? All right. Another thing I wanted to point out to you is since again, of course, obviously we're not coming to class, right, and meeting face to face. You guys are not going to be able, or it might not be easy for you guys to communicate with one another, and that's probably important in the class, right, to be able to communicate with your classmates. So I have opened here, if you click on this discussions link, I've opened a discussion board in Blackboard, so you can make posts to this discussion board, and hopefully some of your fellow students will respond to your posts if you have questions or comments about the class, so you can put those on this general discussion board. I am not going to be moderating this board, however. This is for you guys to communicate with one another, not for communicating with me. So I'm not going to be moderating this, so don't ask questions of me on this discussion board, right? I may look at it from time to time, but not often. So this is sort of your space, right, to ask questions of one another or get in touch with one another, since that may not be easy to do now. Again, since we're not meeting physically together. Let's see, that reminded me of one other thing that I wanted to say when I was talking there, but now I've forgotten exactly what that was. Okay, all right, so if that occurs to me, I will mention it here in just a minute, all right? Okay, so that's just sort of you know, where we are logistically, right, and how the class is going to operate. All right, now I'm going to switch now to the lecture again, okay, and finish our last example on finite probability. So in last time's lecture, right, I mentioned, and I probably had mentioned this before the break as well, that you know, a lot of combinatorics was developed, or at least counting techniques, that part of combinatorics was developed in order to study finite probabilities, because these are the probabilities that are involved with in studying gambling odds in games of chance, right? And of course, games of chance have always been popular, right? And gambling has always been popular, and it turns out that finite probabilities is the key to help us understand gambling odds. And counting techniques are that we study in combinatorics are really crucial to computing finite probabilities. So so games of chance really was a great motivation for the topic of combinatorics, and a lot of the counting techniques that we are studying in the class, that have been studying in the class, were developed in the context of studying games of chance. I wanted to finish here then our just sort of brief foray here into finite probabilities by actually considering finite probabilities associated with a game of chance. And a very popular example of this game of probabilities in the context of games of chance are probabilities associated with the game poker, right? Because those are usually those probabilities are usually easy to understand. So we're going to look at a poker example, and examples like this may already be familiar to you if you have taken a probability class before. All right. you don't really, for those of you who are not really familiar with poker or even with card decks, okay, you don't really have to know all that much, all right? The explanation I'm going to give here will be enough to understand these probabilities, okay? So there are many variations on the game poker, right? But often in a poker game, one is drawing 5 cards from a standard 52 card deck. So we're going to just consider poker probabilities where we're drawing 5 cards, a 5-card poker hand from a standard 52 card deck. Oh, before I come back, I remember what I was going to say just a moment ago. Don't use this discussion forum, right, to try to communicate with me. Use email or, again, or phone or the virtual office hours. But also, you can still send me messages in Blackboard, right? Blackboard messages, not email messages, but Blackboard messages. But I would avoid doing that, okay? Because I don't often see those messages until days after they've been sent, and so this is not a reliable way of getting in touch with me is through Blackboard messages. So I think I probably mentioned that at the beginning of the course, but I want to remind you, if you're going to communicate with me, don't use Blackboard messages. That's not really reliable. All right, okay, so back to poker and poker hands. So in this example, we're going to be drawing 5 cards, a 5-card poker hand from a standard 52 card deck. All right. So again, if you're not familiar with card decks, let me just give you just a brief review of what a standard 52 card deck looks like. Right. So in a standard 52 card deck, each one of the cards has 2 things printed on its face. Right. First is going to be the suit of the card, and there are 4 possible suits, and those are clubs and diamonds and hearts and spades. Okay, so you've got those. Every card is going to be one of these 4 suits, and then also printed on the face of the card will be the rank of the card, and there are 13 different ranks. Okay, so if we list those in, usually how they're ordered is ace would be the lowest rank, and then you have ranks that are numbered. So you have 2, 3, 4, 5, 6, etc. up to 10, and then you have these face card ranks, which are jack, queen, and king. Right. So again, each card in a 52 card deck will have a suit, and it will also have a rank. Okay, so for instance, a card might be the 10 of diamonds, or a card might be the king of hearts, or a card might be the ace of spades, right? Okay, every card is identified by a combination of a suit and a rank. Now, there are 52 cards in the deck, right? Okay, that's because for each rank, right, you have that rank in every suit, right? So you have ace of clubs, diamonds, hearts, and spades. You have 2 of clubs, diamonds, hearts, and spades. You have a 3 of clubs, diamonds, hearts, and spades, right? Okay, so that's how you arrive at 52 cards in the deck. Just take 4 times 13, and that, of course, is the 52, right? So that's really all you need to know about a 52 card deck. That's really all there is to it, okay? All right, so again, in this example, we're thinking of probabilities associated with drawing 5 cards, simultaneously 5 cards, right, from a 52 card deck. All right, so that's going to be the experiment for these probabilities that we're going to compute. The experiment is at random drawing 5 cards from a 52 card deck. So the sample space for this experiment, remember sample space is all outcomes for an experiment, right? So the sample space for this experiment would be all possible poker hands, right? Okay, or all possible, I should say, 5-card poker hands, right? So what are all the different combinations of 5 cards that we could draw from a 52 card deck? That's going to be our sample space, right? And of course, to compute probabilities, we're going to have to be able to count that sample space, right? As you know from Monday's lecture, right? We have to count that sample space, and so that's easy to do, though, in this case. So the size of the sample space, right? The cardinality of the sample space for this experiment. Well, the experiment is just choosing 5 cards, right, from a 52-card deck. So the size of the sample space would be all subsets of 5, right, from this 52 card deck, and that number, right, is just 52. Choose 5. Okay, so we know very well, right, that the ways that we can choose a subset of a particular size, right, from a larger set. Okay, that's this combination. And we know how to calculate, right, this. It's 52 factorial divided by 5 factorial times 47 factorial. And when you simplify that fraction, that works out to be this quantity, 2,598,960. So that's the number of possible 5-card poker hands that one can draw from a 52 card deck. All right, that's the sample space. Now we're going to look at particular events occurring. An event in this experiment will correspond to a type of hand that one draws from the deck. Okay, and these types of hands are, what determine if you, win at the game or not, right? Because certain types of hands are considered stronger than other types of hands. So if you draw a hand of a particular type, right, okay, that might put you in a good position to win the game. Or if you draw a hand of another type, that might not be a winning hand, right? It might not be a hand that you're going to be able to win the game with. All right. All right. So let's start first here with the probability of drawing a type of hand that's known as a full house. Okay. And this is actually going to be a pretty strong hand in poker, right? And what determines the strength of the hand in poker, its its likelihood of winning, is the probability of drawing that type of hand. So if the probability is less of drawing that type of hand, if that hand occurs less frequently, right, in the experiment, then that's considered a stronger hand, right? That puts one in a better position to win the game. All right, now let me explain to you what a full house looks like, right? So when you draw for a full house, what that means is you get 3 cards of a particular rank. So that could be 3 aces or 3 twos or 3 threes or 3 kings, right? So you get 3 cards of a particular rank and then 2 cards of another rank, okay? So if you got 3 aces, then, and you also got, say, 2 tens, that would be 5 cards altogether, right? 3 aces and 2 tens. That would be considered a full house, right? And that is going to be a strong hand because the, as we'll see here, the probability of getting that type of hand is relatively small, okay? Or you could get 3 jacks and 2 queens, right? That would also be considered a full house. Or you could get 3 threes and 2 tens, right? That would also be considered a full house. All right, so so our event here, right, is all possible full house hands, right? And so we want to be able to count, right, all the possible full house hands, right? And then we can determine the probability of this event occurring when we actually draw a hand of 5 cards, right, from the deck, okay? All right, so again, so to compute the probability that this event of drawing a full house, right, actually occurs, right? Remember, that's going to be the size of this set, right? The number of all possible full house hens, right? Divided by the sample space for the experiment. That's all possible poker hands, full house or not. And of course, we already calculated the size of S there a moment ago. That's the 2,598,960, right? Okay. So if we can calculate here the size of E, then we'll be able to compute this probability. All right, so to calculate the size of E, I'm going to think of this, I'm going to do this algorithmically. I'm going to think of a sequence of choices that we can make here in order to build a full house hand, all right? And then I'm going to multiply, right, the number of choices, right, in each step of that sequence to calculate their E. So, all right, so let me tell you here how you can think of this this sequence of choices that one would make to create, right, a full house. So let's see. Remember, a full house has 3 cards of one of these ranks and then 2 cards of another rank, right? Okay. So to start with, let's choose the rank, right, with 3 cards. So that could be, we choose a jack, right, and we're going to get 3 jacks, or we choose an ace and we're going to get 3 aces, or we choose a 3 and we're going to get 3 threes, right? So our first choice there is to choose the rank, right, from which we're going to get 3 cards. So let me see if I can abbreviate that right. Yeah, so we're going to choose, oops, I didn't put the word rank there. So I mean here, choose the rank with 3 cards. Well, obviously, you're choosing one thing out of 13 here, right? So, so the number of ways you can choose that rank with 3 cards is 13. If you want to, you can think of that as being 13 choose 1, right? We're choosing one object out of 13, right? We're choosing one rank out of the 13 possible ranks. But when you compute 13 choose 1, you're just going to get 13. All right, now, let's see, what would our next step here there in building a full house hand? Well, once we've chosen the rank from which we're going to get 3 cards, right, we have to actually choose the 3 cards out of that rank, right? So suppose we decide we're going to get 3 aces. Well, there are 4 aces, right? Okay, and we have to pick 3 of those, right? There are 4 aces because remember you have an ace of each suit, correct? Right? So an ace of clubs, an ace of diamonds, an ace of hearts, and an ace of spades, right? So you've got 4 different ace cards, and you got to pick 3 of them, right? Because remember we want 3 cards with that particular rank. Well, that's again just that's just an easy combination, right? You've got 4 suits here, right? And you have to pick 3 of them, correct, right? Because there's going to be an ace for each of the 4 suits, and you've got to pick 3 of those aces. So this is choose the 3 cards, right? Or you can also say choose the suits of the 3 cards. So once we've done that, right, then we've got we've picked the 3 cards, right, that are going to be of the same rank, right? They're going to be part of our full house. By the way, 4 choose 3, that also simplifies to 4. All right, now, okay, what comes next? Well, we've got part of our hand built, right? So we've got the 3 cards, right, of the same rank. Now we have to pick the 2 cards of another rank, right? So so now let's choose the rank, right, from which we're going to get 2 cards. And now since we've already chosen one rank, correct, and we have to choose a different rank for the 2 cards, at this point now we've only got 12 choices left, right? Okay, because we had 13 ranks to begin with, one of which we've already picked. So now we've got 12 ranks left, right? From which we can choose one of them. And then finally, we have to choose the actual 2 cards, right? So we pick the rank, right, from which we're going to choose 2 cards, and now we have to actually choose the 2 cards, or you can say choose the suits for the 2 cards. And that now is also easy to calculate, right? Because we've got 4 suits, right? We have to pick 2 of them, right? That will determine the 2 cards we pick of our second rank here, right? So this last number of choices here is for choose 2. Let's see, I think for choose 2, that reduces to, when you do this calculation, that's going to turn out to just be 6. Alright, so I'm not going to do the calculations, but that turns out to be 6. And now you just multiply all of those possibilities together, right? And that would give you the size there of our event, right? The event that we draw a full house. Let's see, when you multiply all these numbers together, you end up getting, I'm not going to do the calculations here, but you end up getting 3744. So that's the number of possible different full house hands from a 52 card deck. All right, neat, right? And now divide that by 2,598,960. So you can see that's going to be a pretty small number, right? That's the probability of getting a full house. And actually, if you compute this, estimate this with a calculator, it turns out to be about 0.0014. Okay, very small number, right? So full house hands, right, have are considered very strong hands because their probability of occurring there is quite small, right? Okay, all right. So there's the probability of getting a full house. Let's look at some other poker hands, right? So what's the probability of drawing a straight? And I'll explain to you in a second here what a straight is, but that's pretty much you know what the word says, describes the hand very well, right? And when we can see here if which is a better hand, either a straight or a full house, because the one with the lowest probability is going to be considered the better hand. Okay, I'm going to pause here for a moment, and then I will restart. All right, let's look at a second probability here in poker, the probability of drawing a straight. So a straight means that you get 5 different ranks, right? But they have to be consecutive. So for instance, ace, 2, 3, 4, 5, that would be a straight, or 9, 10, jack, king, queen, right? That would be considered a straight. All right, so but the suits can all be different. You don't have to have the same suit. All right, so let's let our event here be all straights, right? And so let's see if we can count their all possible straights, right? So we can compute this. Probability. Okay, so again, I'm going to think of this, and actually in most of these poker examples, I'm going to think of counting the event algorithmically. So let's think about the series of choices we would make if we were going to actually construct a straight, right? That particular hand. To do that, right, first you would have to pick the starting position for the straight, correct, right? Where the straight could begin. So the straight could begin with the ace, right, or it could begin with the 2, or it could begin with the 3, up to the last possible starting position there, right, would be 9, okay, right, because you could have 9, 10, Jack, King, Queen, right, those 5 cards would also be a straight. So so that's going to be my first choice here, right, is the starting rank for the starting rank, right, for the straight. And if you think of 2 through 9, that number of starting positions, that's going to be exactly 10, right? Possible there, places that you can start that. All right, so and then we have to pick, after we've picked the starting position, right, we have to pick the actual, each one of the cards, right? And so we've actually got to fill, right, the 5 cards, right, into the straight. But remember, those 5 cards can be of any suit, right? Those 5 cards can be of any suit. So, say for instance, you decided to you decided to start with a an ace, right? Okay, then you could have, for instance, the ace of either clubs, diamonds, hearts, or spades, right? It wouldn't matter which suit you started with. And then you could have 2 of clubs, diamonds, hearts, and spades. And then you could have 3 of also clubs, diamonds, hearts, or spades, okay? So, so in picking each card, right, okay, you're really just picking a suit for each one of the cards, because you can have any of the 4 suits, right, for each of the cards, right, in your for each of the cards in your straight. So so pick a suit for the first card, you got 4 choices there. Pick a suit for the next card, you got 4 choices, and so on and so forth. And then just multiply all these choices together, and you get 10 times. That's 4 to the 5th power. When you actually calculate 10 times 4 to the 5th power, that turns out to be 10,240. Okay, right, 10,240. So the probability of getting a straight is 10,240 there, divided by, again, that number of different poker hands, right? I forgot what that was. So 2,598,960 again, and that turns out to be approximately 0.0039. So notice you have a low probability of getting a straight, so that's a strong hand, right? But it's a higher probability than the probability of, oh, is it? Oh, no, okay. It's a smaller probability. Oh, no, it is. It's a higher probability than this probability of getting a straight is a higher probability than getting a full house, right? So a full house is considered a stronger hand in poker than a straight is. Well, I want to explain something that I didn't explain well just a moment ago for the starting rank. So I mentioned, okay, so we can start our straight at ace, or we could start at 2, or we could start it at 10, up to 9, right? So that's actually 9 different starting positions for the straight. But another way to have a straight is if the straight wraps around as follows. You could have a 10, a jack, a queen, and a king, and an ace. That would also be considered a straight as well. So that actually gives you an extra possibility there for, that also allows 10 as a starting position for a straight. So that's why we have 10 different, starting ranks there for the straight rather than 9. All right. Now, an even stronger hand in poker would be a straight flush. So that would be a straight where, you have 5 cards, right? 5 ranks in a row, correct? So that's a straight. But if it's a straight flush, that means all of the cards are going to have the same suit, right? All of the cards would have the same suit. So all of these choices here for picking different suits for the different cards are eliminated, right, in a straight flush. All of the cards would be the same suit. For example, a straight flush could be ace of clubs, 2 of clubs, 3 of clubs, 4 of clubs, and 5 of clubs, right? Okay, that's a straight flush. All right, all the cards in the straight have to have the same suit. Well, so it's here it's much easier now to calculate the probability. Okay, because it's very easy here to count the size of E in this setting. All right, just like with a straight, right? You have to pick the starting rank, right? So there are 10 possible starting ranks, but then you don't get a chance to pick a suit for each card, right? You can pick a suit for the first card in your straight, but then all the other cards have to have the same suit, right, to make this a flush. So pick the suit for the first card, and then all of these other cards in the straight are determined. So you really only have 40 possible straight flushes. So the probability of a straight flush is very small, right? That's just going to be 40 divided by the 2,598,960 possible poker hands, right? And that is approximately, wow, it's a really tiny number here. It's 0.0000154. So a straight flush is a very, very strong hand, right, in poker, because it has a very low probability of actually occurring. All right, just 2 more examples, and then we'll be done. Let's see the probability of drawing exactly 2 pairs. So this is similar to a full house, but not quite the same, right? So you have 2 cards of a rank, and then 2 cards of a different rank. So that could be, say, 2 5s, and then 2 queens, or 2 jacks and 2 aces, right? So a pair of one rank and a pair of another rank, and then the third card is something completely different. So it's not the same rank of either of the pairs, correct? Right. So you have a third card which has a different rank from the first 2. So in computing the probability here, this seems like computing the probability of a full house, right? But I want to show you that you can get into trouble doing it that way. All right, so let's let E be the event that we have a hand with exactly 2 pairs. So what are all possible hands there with exactly 2 pairs in them? All right, so if we treat this like creating a full house, let's recopy there our full house description and see if we can use that. Alright, so we're thinking, let's see, first we would choose one of the ranks, right, for one of the pairs, right? So choose a rank there with 2 cards, right? Okay, so that would be, say, the first pair, correct? And so we can figure out, how many ways we can do that. And then next, we would also choose the suits, right, for the next pair, right, for the next 2 cards. No, I said that wrong, right? So, choose the rank for the 2 cards, right, and then choose the suits for those 2 cards, and then next choose the rank, right, for our next pair, correct, and then choose the suits of our next pair, right? Okay, and then I guess we would have one more choice here, and that would be to choose the rank there of the last card, right? Because we've only got 4 cards filled in to our hand here at this point. So again, I'm trying to just mimic here creating exactly 2 pairs like I created a full house, right? Because exactly 2 pairs is kind of similar, right, to a full house, right? So first choose the ranks of the first pair, right? Okay, and then choose those 2 cards that are going to go into the pair, and then choose the rank for the second pair, right? Okay, and then choose exactly which 2 cards are going to be in that second pair, and then you have to choose the last card, right? So that's just a matter of choosing the rank of the last card. One more choice here, right? So we have to choose the rank of the last card, right? And then we also have to choose the suit of the last card. Unfortunately now, this is not going to work, okay? So if you try counting the number of hands that have exactly 2 pairs with them in this way, you're going to end up with overcounting. And that's because choosing the first pair is going to be symmetric to choosing the second pair, right? Okay, so if you choose them in order like this, choose the first pair and then choose the second pair, you've taken the order of how you're choosing the pairs into account. But because we have a first pair and a second pair, but in a poker hand, the order of the 2 pairs in your hand is not important. It's just that you have 2 pairs, okay? So, see, in this scheme of counting, let's say we decided to choose 2 2s first, right? And then 2 3s next, correct? And then some other card for the remaining card, all right? We would be counting different than choosing the 2 3s first and then choosing the 2 2s second. In our scheme of counting, choosing 2 2s first and then 2 3s second would be different from choosing 2 3s first and choosing 2 2s second. But that is really the same hand, right? In poker, you still have 2 2s and 2 3s. So this this method of counting here, the two pairs, is going to overcount. Here. All right. Trying to count the two pairs like we counted full houses is that's not going to work. So we're going to simplify this a little bit, actually. Okay. To get a scheme that is actually useful. All right. So so the first choice we're going to make there is instead of choosing the first pair first, we're going to choose the ranks for our two pairs. So we're going to decide first, are we going to have two tens and two jacks? Are we going to have two queens and two kings? Are we going to have two aces and two twos, right? Or are we going to have two threes and two fours? So first we're going to choose the two ranks that are going to form the two pairs, right? So you've got 13 ranks, and we're going to choose two of them out of those 13. Okay, so that's our first choice here. So it's choose the two ranks for the two pairs. And the way you can do that, of course, is there's 13 ranks, and we're going to choose two of them. Okay. Now, once you've done that, now choose the two suits, right, for the two ranks. So choose the two suits that are going to be involved in the for the two ranks. And the way you can do that, obviously, is for choose two, right? Because there's going to be four suits, right? And you're going to choose two of them, right, for your two ranks. Okay, so let's see what that would give us at this point. All right, so first we choose two ranks. So let's suppose we choose ace and two, right? Those are going to be the two ranks that we're going to pick. And now let's choose the two suits, right? For the two ranks, right? So I choose next, let's say, clubs and diamonds, right? So what hand there now would that correspond to for us? Whoops. I don't think I said that. I don't think I said that exactly right. Let me try that again. Let me pause here for a second. Okay, let me try to explain that again because I didn't explain that well the first time I tried there. So to get exactly two pairs right, to form a hand with exactly two pairs right, again, we're going to choose the two ranks for the two pairs, right? So for instance, we could choose the two ranks as ace and two. So we've decided that we're going to have a hand with two aces and two twos in it, right? And then the last card would be something other than an ace or a two, okay? So there's our first choice in our sequence of steps to build that hand with two pairs in it. Now, next we have to choose the two suits for the first pair, right? So suppose that ace is going to be one of our pairs. Then we have to choose the two suits, right, that we want for ace, right? So that could be clubs and diamonds, or that could be hearts and spades, right? Or that could be clubs and hearts, correct? So so there's four choose two ways, right, of choosing those two suits for the first pair, because there are four suits altogether, and we have to choose two of them because we have a pair of cards, right, that we have to assign suits to. And then we can also choose the two suits for the second pair, so that would also be two ways of doing that, right? Okay, so for example, again, suppose we have ace and two. Where did I put it there? Suppose we have ace and two as our as the two pairs, right? So for the ace, we have to pick its two suits, so that could be clubs and diamonds, for example. And then for the two, we also have to pick two suits, right? That could be, for instance, clubs and hearts, right? So we could have this hand where we have an ace of clubs and an ace of diamonds, and then we have two of clubs and a two of hearts. So that would be, and then a hand with two pairs. And then you've still got, that's only four cards, right? So you've still got the last card to fill up. But the last card cannot be either an ace or a two, right? So you've got to exclude all aces and all twos when you make your choice for your last card. Well, there's four aces and four twos. So, for instance, there's going to be four cards of the first rank, and then there's going to be four cards of the second rank, right? So you have to exclude those two cards from your when you choose the last card. So that leaves you 44 cards left, right? 52 minus 8 is 44. So just multiply all these together, right? And that is going to give you the number of hands that have exactly two pairs in them. So the probability of this event turns out to be, again, of course, always, right, the size of the event divided by the size of the sample space. When you multiply all these numbers together, let's see, that turns out to be 123,552, and we're dividing that again by that large denominator, 2,598,960. And when you get a decimal approximation for this, it turns out to be about 0.048. So so you can see that the probability of getting two pairs is higher than the probability of getting, for instance, a full house, or the probability of getting a straight. So this is a weaker hand than a straight or a full house in poker, right? It still could be a winning hand, but it's not as strong a hand as a full house or as a straight, for example. All right, let's finally do this last one, okay? And so let's see, what's the probability that we draw at least one ace, okay? So at least one ace, all right? And oh, wow. So that sounds like, let's write our event there. So again, this is all hands, right, with at least one ace. So notice that the complement of this event, right, is going to be all hands without an ace, right? And so we can calculate the probability or the size of E, right, or also the probability of E, right, by complements, all right, because it's pretty easy to compute the size of the complement of this event, right? It's pretty easy to calculate the size of or the number of hands here without an ace, right? Because if you have a hand without an ace in it, that means then that what you're really doing there is choosing the 5 cards from the 48 cards that are not aces, right? So hands without an ace would be, the number of those would be 48 choose 5, correct? Because you've got to choose your 5 cards from the 48 cards that aren't aces. Okay, so this is going to be as you know here, right, 48 factorial over 5 factorial times 43 factorial, and when you simplify those computations, I think this turns out to be rather large there. It's 1,712,304, okay? And so that what that means is that the size of the event that we're interested in, all hands with at least one ace, right, is going to be just all hands, right, which was what was that, 2,598,960, 2,598,960 minus this 1,712,304. And that turns out to be, if you do that subtraction, 886,656. Okay. So there are, since there are this many hands that do not have an ace, right, then there must be this difference, or 656 hands, right, that do have at least one ace in them. So the probability that when you draw a hand that you get at least one ace is going to be pretty good, right? 886,656 divided by the 2598960, and that's approximately 0.34. Oh, so I see you have about 1/3 chance, right, of getting a hand with a 5-card poker hand with at least one ace, or about 1 out of 3 5-card poker hands will have at least one ace in them. Okay, let me pause there for a moment because we're through there talking about finite probability, and for at least for a little while here talking about counting techniques. So we've really spent a lot of time talking about those. You've gotten really quite expert at counting sets, not completely, but quite expert at counting sets. We are going to get back to more advanced counting techniques eventually, but first we're going to take a little bit of a detour into a different topic in combinatorics that's not so counting intensive. All right, so when we come back, we'll maybe start that topic. I mentioned one other problem here in this part E of this poker example, and so we just calculated the probability that we get at least one ace. And so I'll just leave this as a question for you. How about what's the probability that we would get at least 2 aces, right? So instead of at least one ace, at least 2 aces. I think you can solve that problem also with complements. A little bit more difficult example, but you can solve that also with complements as well. All right, let's start our next topic. I don't want to get too far into this today because we're going to run short of time, and I don't want to run over time. But so today's topic is our next topic is going to be the Pigeonhole Principle. You may be familiar with the Pigeonhole Principle already, because this is really one of the most frequently used tools of reasoning. All right, so this is really an important tool of reasoning. It's not just a part of combinatorics, but because it's loosely related to counting sets, it's considered often part of combinatorics. But it's really just a fundamental principle of logic and is useful in really all branches of mathematics. Will make use at one point or another of the Pigeonhole Principle. And then, once we've talked about the Pigeonhole Principle, we're going to look at a generalization of the Pigeonhole Principle, a really profound generalization of the Pigeonhole Principle called Ramsey Theory. All right, and so this is kind of a really fun topic here, Ramsey Theory, but it's related to the Pigeonhole Principle. All right, let me state the Pigeonhole Principle for you. So there are lots of colorful ways of stating the Pigeonhole Principle, and I'll explain where the where the principle gets its name from. So suppose we have n plus 1, so n is just a positive integer here, right? And we want to, so n plus 1 objects, and we want to distribute them into just slightly fewer boxes, okay? So we've got n plus 1 objects, but we're going to distribute those objects into n boxes, all right, in any way. So slightly more objects than we have boxes, right, in which to put the objects. So you can think of the objects as being pigeons, and we're going to put those into pigeonholes, okay? I don't know when anyone actually puts pigeons into pigeonholes. I guess pigeons put themselves in pigeonholes, right? But anyway, this is where the using pigeons as the objects and pigeonholes is the boxes. That's where the pigeonhole principle gets its name. And so so that's the setting. And so if that's the activity that you're going to perform, putting those n plus 1 objects into n boxes, then what this principle says is that one of those boxes is going to contain 2 or more objects, right? So that seems like a fairly straightforward idea from logic, right? You've got more objects than boxes. And so one of your boxes is going to have more than one object in it, correct? Okay. So again, this is a very standard idea, right, from elementary logic. Okay, and so it's useful in lots of right, in lots of different settings, not just in combinatorics. Actually, one can prove the pigeonhole principle, right? So let's actually give a little proof of this, but it's an easy proof because, again, this is a very straightforward logical idea, right? So and our proof is going to be by way of contradiction. So suppose that we make the distribution of the objects into the boxes, and we don't have more than one object in any box. So suppose each box has just, at most, one object in it, right? Okay. Well, then you can just count the objects easily, right? Just go to each box and count how many objects are in each box. You've got n boxes, but we're assuming, by way of contradiction, right, that each box has at most one object in it. So that means then that you can have at most n objects, correct, right? Because if you've only got n boxes and each box only has at most one object in it, then you can't have more than n objects. But that's a contradiction of the assumption, right? Because we were assuming that we started with n plus 1 objects. So easy contradiction proof, right, of the pigeonhole principle, right? So again, what the pigeonhole principle says, right, is you've got n plus 1 objects, right, and you're putting them into a slightly fewer number of boxes, right, then one of the boxes is going to have lots of objects in it, or one of the boxes is going to have more than one of the objects in it, right? Okay. So let's just apply that quickly to one very simple example. So suppose we choose students at random from the class, right? Okay, from our class. How many should we choose to guarantee that 2 of them have the same major, right? Okay. All right. So so if we start to choose students from the class at random, how many must we choose until we know that we have chosen 2 students with the same major? All right, well, guys, in this example, you are playing the role of the pigeons, all right? Because what I'm thinking of doing here is taking you and putting you into boxes that correspond to our different majors in the class. And remember, recall, right from the beginning of the semester that we had 5 different majors, right? I think, right? I think it was 5. I'm going to assume it was 5 represented in the class, right? And so if I start stuffing students right into these boxes that correspond to these majors, correct, then eventually, right, it has to be the case that I have more than 2 students in the same major, right? And so, well, how many then must I pick to guarantee this? Well, the pigeonhole principle says that's got to be one more than the number of boxes that you have, right? So if I pick 6 students, right, from the class, then 2 of them have to have the same major, correct, right? So if we start picking students at random, right, we might pick a student in major 3, we might pick then the second student in major 1, we might pick the next student in major 4, and then the next in major 5, and then next in major 2. So if I just pick 5 students, I might get 5 different majors, right? But when I pick the 6th student, correct, I'm going to have to duplicate a major, right? Okay, so could be major 3 or it could be any of the majors, right? We're going to have 2 students at least, right, with the same major at that point. So see, there's a very simple application, very elementary application there of the pigeonhole principle, which is itself kind of an elementary idea from mathematics. There are lots of different ways of restating the pigeonhole principle. And let me just show you a couple of them before we looked at some more advanced applications of the pigeonhole principle. So here's another way of stating the pigeonhole principle. If n objects are put into n boxes and no box is empty, right? So boxes are put into, if n objects are put into n boxes and no box ends up empty, then that means each box contains one object, right? Or if n objects are put into n boxes and no box gets more than one object, then no box is empty. That makes sense as well, right? Okay, so those are just simple restatements of the pigeonhole principles. All those ideas are related to each other, right? All those elementary logical deductions are related to each other. They're all versions of the pigeonhole principle. All right, so in next Monday's lecture, we're going to have fun because we're going to look at more advanced applications of the pigeonhole principle. And then, again, as I mentioned, this important generalization of the profound kind of generalization of the pigeonhole principle referred to as Ramsey's theorem. And then there's lots of stuff related to Ramsey's theorem, which is called Ramsey Theory. Okay. All right. So I will have your next lecture ready on Monday the 30th, and remember that is when your homework 4 is going to be due. Visit me in my virtual office hours, right? Anytime you need to ask questions about that homework assignment or anything else. Okay. All right. So I'll see you all on Monday. Best wishes for the weekend. Stay safe. Do not touch anything. Okay. And if you do, wash your hands.